Howdy, people. We're going to start transitioning from our discussions of electrostatics, electrostatic forces, and electric fields into electric circuits. All right, and we're going to start by, um, well, going back to a representation of what you see here on the left, and that is the electric field created between two oppositely charged parallel plates. All right, in here is what we call a uniform electric field. All right, and what that electric field can do is if there are charges placed in this field, here's a negative charge, here's a positive charge, well, this field would push this positive charge that way, it would push this negative charge that way, and the amount of push would be based on how strong the field is and what the charge of each of those objects is. All right, now, how did these plates get charged? Well, not by themselves. They got charged because electrons were removed from the positive plate and electrons were deposited on the negative plate. And maybe those were the same electrons. Maybe the electrons were taken off of here and dumped onto here. All right, and how do we do that? Well, we can do that by using an object or a thing whose job is to push electrons around, and one of those things is called a battery. All right, and so if I have a battery that's oriented like this, here's that like a big old D cell battery that's oriented like that, where the little nub end on the left is the positive terminal. Well, what did happen was electrons that were over here got attracted to this positive terminal, and that this battery can take electrons and push them away from this negative terminal and onto that plate. And so we could create this electric field between two pieces of metal by connecting a battery to each of the plates. All right, and then that if we could put charges in that field, the field would push the charges around. Let's think about this in a different way. What if we had a whole bunch of charges and we wanted to move them around? Well, I mean, this field, by its nature, it can move charges around if charges are in the field and able to be moved. And so if we think about this a little bit differently, imagine taking these two plates, right, and connecting them with not just empty space, but a thing that's full of charges that can move around. All right, and that thing is called a wire. So imagine this, right? You take, here's the one plate, here's the other plate, and they're connected by a wire. That's like a metal wire. All right, and then we, like bend this thing up like this and bend this end up like that, and here's the one plate and here's the other plate. You get what I'm saying? And then we bend them around again, and here's the one plate and here's the other plate, and here's the wire. You get what I'm saying? And look, this now the field that was going like this through between our positive and our negative plate is now, the field can be made to point through that wire, where this is our positive terminal and that's our negative terminal. And look, it's kind of just like that. All right. So what is a battery? A battery really is a source of what's called positive potential and negative potential that creates a field. And what we let that field get created in is something that has lots of electrons in it that are easy to move around, and that thing's called a conductor. All right, a conductor is a wire. All right, so what we're going to talk about is, by its nature, here I'm going to draw a simple what's called schematic representation of a circuit. Schematic, just fancy word for drawing. All right, here's a fancy schematic of a battery. Instead of drawing a cylinder, that's the electrical symbol for a battery. And so here's a wire. Let me make things with nice kind of square corners because it looks pretty, I guess. So this is a really, unuseful circuit. All it is a battery with a wire connected from one end to another. And remember, what's a wire? A wire, by definition, is a conductor. What's a conductor? A conductor is a substance that has lots of electrons in it that are easy to move around. All right, so this conductor is filled with electrons everywhere, tons, 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 tons. They're easy to move around. You know what I should do is I should say, well, imagine that there was some part of this circuit that we could disconnect and connect when we felt like it. We can swing this little door shut. That's called a switch. All right, and as soon as we close that switch, well, what happens is there's an electric field that's created everywhere in this wire that points from that positive terminal. This is called the positive terminal of the battery. The field goes from positive to negative, so there's an electric field that points this way. You don't typically draw that field, but it's there inside a wire. And what does that field do? Well, because there are charges everywhere in the field pushes the charges, and then these charges all start to move. They all start to move this way. Right? The field is counterclockwise, but this electron current would be clockwise because remember, the whole idea of what directions the field point, it points in the direction of the force that a positive charge would experience, but our charge movers are actually negative. All right. Now, in a lot of cases, a circuit like this doesn't do anything. All it does is move charge. We usually move charge so it will, I don't know, light up a light or heat up a heating element or make a sound, make a bell ring. This circuit doesn't do anything except move charge. All right, and then the question is, so how fast does that charge move? Well, that depends. All right, it depends on a characteristic called resistance. All right, so this introductory thing here is sort of about, you know, in a very basic sense, what a battery does, and that is create an electric field inside a conductor. What a conductor is, well, a conductor is basically a tube filled with electrons that are easy to move around. And then resistance is about how easy or difficult is it for those electrons to move. All right, so let's talk a little more in depth about the resistance of a conductor. A conductor, again, aka a wire. In the context of circuits, at least, conductors are wires. Wires are made of metal. All right, and this is like a, you know, this is a zoomed in section of the wire. A nice straight section of wire. Now, this wire and all wires have some amount of resistance. All right, so resistance, let's define as the extent to which a conductor inhibits the movement of charge. We've actually just defined something else. Movement of charge. We call that current, electrical current. So resistance is the extent to which a conductor inhibits current. It's easy to say the extent to which it resists, but that's kind of a circular definition. Resistance is how much it resists. So I use the verb or the adjective, inhibits, kind of like resists. All right, so every conductor, every wire has some resistance to current. All right, and that resistance depends on a couple of mathematical characteristics. What I mean is physical dimensions, really. So it depends on the length of the conductor, and in particular, the longer a conductor is. Let me do this to keep with the conventions of how I normally say this sort of stuff. The longer a wire is or a conductor is, the larger the conductor's resistance. So resistance is proportional to length. All right. Resistance, we use the variable capital R. It's measured in things called ohms, and an ohm we abbreviate as a Greek capital omega. So a conductor's resistance is proportional to how long it is. The longer the wire is, the more resistance it has. Um, but then there's this other measurement, physical measurement, that we can look at, which is what's called the cross-sectional area, A, of the wire. And the fatter a wire is, the larger the area is, the smaller the resistance. So that says R is inversely proportional to the wire's cross-sectional area. So a short, fat wire has low resistance. A long, skinny wire has high resistance. Imagine trying to drink something through a straw. If it were a very long, skinny straw, it would be difficult. If it were a short, fat straw, it would be easy. Sort of the same thing, at least sort of analogous. Now there's this other, so that sort of leads us to an equation that, well, we have directly related to L, inversely related to A. And that's pretty close to it, except there's one other thing that affects how much resistance a conductor has, and that's what the conductor is made of. All right? And that is captured in a property of matter called resistivity. That is a different word than resistance. There are many of the same letters, I do agree, but it is not the same thing. Resistivity is a fundamental property of substances, okay, and in particular of conductors. And it's on the atomic level, has to do with how easy it is for electrons to actually move around. All right, and so this is, I'll say, a characteristic of the substance slash material from which conductor is made. Check it out. This is a page on the New York State Regents reference table for physics, and down here in the electricity stuff. Oh, look, a bunch of different resistivities at 20 degrees Celsius. So that's room temperature-ish, which also says that resistivity actually depends on temperature, which means that resistance depends on temperature. We'll come back to that in a second. But here are some standard, I don't know. Here are some things that many wires are made of. Aluminum, not so much anymore. Copper, sure, lots of. Gold, good stuff, and so on and so on. So here are resistivities. They're measured in ohm meters. We'll just derive why that is. And okay, sure. So that's a reference. You know, you've seen some types of situations where they'll say like, hey, a steel drum is on the back of a steel truck, and that tells you, oh, that's a coefficient of friction thing. That's about materials. Well, sometimes now in the context of conductors, you'll say, well, or a problem we'll talk about, a wire is made of copper and you're saying, aha, made of copper. I should refer to my resistivity chart and plug that number in as appropriate. Okay, so you'll be provided, those aren't things to memorize, of course, that's why they're in a reference table. So here is our equation for resistance, for a conductor's resistance. And let's just be sure that we can nail down the unit stuff, right? Of course, length measured in meters. Of course, area measured in square meters, meters squared, right? Like if this is a cylindrical wire, of course, that area is pi r squared, meters squared, right? And so if we just algebraically solve for resistivity, we get R A over L, which has the units of ohm meters squared per meter, thus the ohm meter. Fair enough. Now, we should also just make sure we say here that resistivity depends on temperature. And higher resistivity means higher temperature and thus higher resistance. All right, we don't need to know a quantitative relationship there. You just need to know that if conductors get hot, their resistance goes up because their resistivity goes up. All right, you may have heard of some superconducting things, and superconductors have to be cooled way the heck down to lower resistivities. Okay, so here is an equation that you should be prepared to use in some situations that talk about here's a wire, what's its resistance, and or here's its resistance, what's its length, and or here's its area, what's its, you get me? Or once in a while, what's the wire made of? You'd refer back to your table of resistivities. Got it? Okay, farewell.